Hi, this is today's lesson on the evolution of high mass stars. I'm going to talk about how these stars evolve from first reaching the main sequence all the way to eventually their demise. Now, so far we've talked about low mass stars and medium mass stars, the low mass stars being the red dwarfs, which really don't do much beyond first nuclear fusion. Um, Really, they're fusing hydrogen into helium in their cores. In fact, it's such a slow pace that even today, the first red dwarfs that formed are still alive today. The medium mass stars are a little more interesting, unlike the red dwarfs that'll end their lives simply turning off in the cores, contracting to become white dwarfs. The medium mass stars at least evolve into giant stars. They become red giant stars, go through a few different transitions while in the giant phase, and then shed their outer layers to reveal their core and become a planetary nebula and eventually a white dwarf. Now, with the high mass stars, we're going to see that their end involves not so gradual a demise, but a very chaotic and explosive event that we call a supernova. Now, it doesn't mean that we get the same result each time. A supernova, meaning, very intense new star, is actually the death of a star. And we will see that all supernova are not equal. So again, starting with the high mass stars. In terms of their basic properties, we're basically going to define high mass stars as stars that are about 8 times the mass of the Sun, up to maybe 100 times the mass of the Sun, although we do have some evidence that stars get even more massive than that. We will talk briefly about stars that may be 4 to 8 times the mass of the Sun, but those actually act a little more like medium mass stars. They're sort of in the gray zone between a star that is going to end its life as a white dwarf, a star that's going to end its life during a supernova explosion. Now, all high mass stars heavier than our Sun, will have much shorter lifetimes. Okay? Really, if you remember, that stars are balancing the gravitational pull that's trying to cause them to compress with thermal energy. You understand that a heavier star is going to have a much more intense gravitational field, especially pushing on the core. This is going to cause the core to need more energy to prevent itself from collapsing, and it means that it's just going to burn a lot hotter and it's going to burn a lot quicker. Now, interestingly, most high mass stars can synthesize just about every element in the periodic table. They can synthesize all elements up to iron up until their final day. And then it's actually the supernova that ends up allowing it to produce even heavier elements. So these stars will start on the main sequence as very hot blue stars. Will eventually expand to become supergiants and then end their lives as supernova. Now again, high mass stars, for the most part, formed by the same processes as low mass stars. They enter the main sequence anywhere from B8 on the Harvard spectral scale. And if you remember, a higher number corresponds to a slightly cooler star. So they start sort of as a cooler B-class star all the way up to the hottest possible class, and that's 05. I do want to say that, again, during their formation, they would form about the same way as our Sun did, up to about 20 times the mass of the Sun, where we now think that anything above 20 times the mass, or maybe even 30 times the mass of the Sun, would need several stars to actually merge together. So stars forming at very large masses are extremely rare. Okay? And the largest of the large stars are the rarest of all the stars that we see, just because they require very, very specialized conditions. we need to form a lot of very big stars close together, and they need to merge together according to current theory. Now, all stars, when they stabilize hydrogen fusion in their cores, when the cores start to get going, okay, they settle somewhere on the main sequence. We've already seen that low mass stars settle here, medium mass stars settle here. So the highest mass stars will settle somewhere from here to about here. And basically, they're going to spend a very short time on this main sequence compared to the other stars. Again, high core and surface temperatures are really what are going to keep these stars from collapsing inward. Now, the interior of these stars is slightly different from what we see with the low mass and even the medium mass stars. What we see here is a core at the very center, but instead of a radiation zone around the core, we have a convection zone around it. This is basically due to the extremely high densities and pressures at this level, that radiation has a very difficult time getting through there, and therefore it begins to convect. Now, the radiation zone for these stars extends all the way almost to the surface. Okay? These stars are hot enough to basically transport energy from the region around the core to the surface, as long as the density gets low enough, through basically X-rays, through radiation. Now, here's what's surprising. We have to, again, compare it to what we see with stars like our Sun. The basic benchmark that we use in comparing stars is always our Sun because it's the one we're most familiar with. According to current theory, our Sun would spend about 10 billion years on the main sequence. Compare that to a star of 4 times the mass of our Sun. This isn't even in the high mass and that we're going to talk about later. There it only spends about 100 million years. At 5 times the mass of our Sun, 65 million. Now, really, when we're getting up to the true high mass stars, like around 9 solar masses, 21 million years. Compared to our lifetimes, that's very long. But again, compared to our Sun, that's a fraction of the lifetime of our Sun. Okay? Our Sun lives on the main sequence for almost 500 times longer than one of these stars. Okay? Again, 10 billion compared to 21 million. That's a factor of almost 500. Gets even worse. When we get up to 15 solar masses, those stars are on the main sequence for 1,000th of the lifetime of the Sun. Okay? If you had our Sun burning, or on the main sequence, it would last the equivalent of 1,000 of these high mass stars. Now, of course, these short lives mean that they're going to glow very, very brightly. Even though it only lives 1,000th of the total time of our own Sun, it actually puts out 16,000 times more energy. Of course, the rarest of the stars, the highest mass stars, will last even less than 100,000 years. Okay. What are some of the things that we see with these stars besides just their short lifetimes? Well, while on the main sequence, these stars have very, very high surface temperatures. The high surface temperatures mean that there's going to be a lot of thermal pressure, not only supporting the interior of the star, but also thermal pressure pushing the outer layers of the star away from the star. This produces a very intense stellar wind. Now, for our Sun, we have a moderate solar wind, or probably even a light solar wind. But for these very massive stars, the high temperatures produce intense stellar winds. And this really ends up taking away a very significant fraction of the star's mass. Our Sun doesn't change very much in terms of its mass with the solar wind because it's so much more massive than the atoms it's giving out. But in some cases, with these supermassive stars, they may lose almost half their entire mass due to these intense stellar winds, even before they leave the main sequence. Now, these cores of the massive stars, again, have to be very hot, have to be very energetic, okay? It's like a race car engine. It's consuming fuel at a very fast rate to support the intense gravitational pressures. Now, when the core runs out of hydrogen, it's no longer going to have a source of energy. So gravity is going to win and cause it to shrink. As it rapidly shrinks, it also rapidly increases in temperature. The helium in the core eventually becomes hot enough for fusion of helium to occur. A new layer of hydrogen surrounding the core ignites. This is what we saw with the medium mass stars. However, the difference here is, unlike the medium mass stars, these very massive stars will actually remain hot enough in the core where the core never becomes degenerate. Now again, once these stars run out of hydrogen in the core, they begin to evolve. They begin to move away from the main sequence. They actually get brighter, which means that they're moving up on the HR diagram, and cooler at the same time. This means that their outer layers are basically expanding as their cores are shrinking and getting hotter. Eventually, they become supergiants and burn very, very intensely, more so than they did on the main sequence, but also for an even shorter period of time than they did when they were main sequence stars. Now, once again, after the stars use up the hydrogen in their cores, they're going to move on to fuse even heavier elements. Remember, all stars start out by fusing the element hydrogen, shown here by the letter H. They convert this hydrogen into helium. Now, eventually, as the helium accumulates in the center, the core becomes dense enough, it becomes hot enough, and it lacks hydrogen, so that part of the core begins to shrink, and then that'll fuse heavier elements. All these peaks that you see here, and this is a logarithmic scale, which means it goes up by powers of 10, show the relative abundance of elements in the universe. In a large respect, the abundance that we see here is really a relic of these massive stars that have come before our own sun and then exploded, dumping their elements into space. Helium produces carbon. Helium fusion also produces oxygen, neon, and everywhere you see a spike here corresponds to an element that is basically produced in the cores of these stars. Okay? Anything heavier than helium was created inside a star. Now, going back to when it was on the main sequence. Once again, as it fuses hydrogen into helium, it is relying on something called the Cnl cycle. In our sun, most of the hydrogen fusion that takes place are simply hydrogens fusing with hydrogen, making deuterium, deuterium making helium-3, and then helium-4. In this case, carbon, nitrogen, and oxygen actually act like a catalyst. Hydrogen goes into the reaction, okay, and helium comes out of the reaction. So as hydrogens are added during different phases of this, it makes the initially carbon heavier into nitrogen. The nitrogen eventually becomes oxygen, and then it's converted back into carbon again as the nitrogen is hit by hydrogen. So basically, this production of helium again continues for these supermassive stars for the beginnings of their lives. Once the hydrogen is used up in the core, a layer of hydrogen will fuse around the core of the star, and new reactions take place. The first reaction is called triple alpha. The helium nucleus is actually what is also called an alpha particle. So triple alpha means 3 helium come together to produce 1 carbon. Another reaction that can take place in the helium core is helium and carbon, carbon being the byproduct of triple alpha, can produce oxygen. Likewise, the oxygen can combine with other helium and produce neon. So these 3 elements that you see, carbon, oxygen, and neon, are actually byproducts of the second phase of fusion. Eventually, the star is going to run out of helium in the core, Now a new, heavier core will begin to fuse elements. It'll fuse elements, for instance, oxygen can produce silicon, oxygen can produce sulfur. It'll keep producing progressively heavier elements until we get all the way up to iron. When we reach iron, we've basically reached the end of the road. See, the problem with iron is, iron, instead of adding energy and allowing the star to support itself against the gravitational pressure, actually takes energy away. It's what's called an endothermic reaction. And this is what's going to cause a star to basically fail. It's going to cause the core to collapse, and it's going to produce one of the most spectacular events that we see in the universe, the supernova explosion. Okay, so that's where we're headed with today's discussion. Let's look at stars of different masses and see how they might deviate from one another. Now, one topic that is, could have fit with the last lesson, but we're putting it here, are the stars that are somewhere between being of medium mass and high mass. These are stars from about... Now, these stars can actually go one of two ways. They can end their lives like medium mass stars end, producing a planetary nebula, or they can end their lives as a supernova. It really depends on a lot of different things during the star's life. Now, stars between 4 and 9 solar masses, some of the models have the core of the star fusing just a little bit further than the medium mass stars. Remember, the medium mass stars would basically fuse hydrogen into helium, and then helium into oxygen, and helium into carbon, oxygen, and neon. And that's basically where they would end. These stars could actually have an additional reaction called a carbon flash, and this would produce everything from oxygen, neon, and magnesium. Now, basically, two things could happen. Either the core could basically destabilize the rest of the star, shed the outer layers, and leave behind a white dwarf. Or what could happen is essentially we could end up having the star go supernova. Now again, the fusion of carbon is really much less efficient than the fusion of hydrogen or helium. Okay? But it does produce the heavier elements that we talked about. It can produce oxygen. It can produce neon. It can produce magnesium. If this reaction is successful in shedding the outer layers, the star will not become a supernova. Instead, it will become an oxygen, neon, magnesium white dwarf. Now, the white dwarfs that we talked about for the medium mass stars were basically mainly made out of carbon. In these types of stars, all the carbon has been basically fused, and what we're left up with is oxygen, neon, and magnesium. The problem is the core has to leave behind a white dwarf that is less than 1.4 times the mass of the sun. Okay? If it doesn't, the star will go supernova. So really, the fate of a massive star, somewhere between being medium and being high mass, depends on, whether or not it can get rid of enough mass in its giant phase. So stars between 4 and 8 solar masses may be able to end their lives as white dwarfs, or they may end up as supernova, depending on how much mass that they can get rid of. And a lot of this depends on metal concentration. Are there a lot of heavier elements in the atmosphere which would make it easier to push the atmosphere away? Again, if what is left over is less than 1.4 solar masses, we get a white dwarf. If something left over is greater than 1.4 solar masses, the core collapses and we get a supernova. All right. Sorry that's a little bit muddy, but sometimes the stellar evolution is not the easiest. Well, it's one of the more complex processes that we have in nature. In any case, let's go into something that's a little more concrete. Stars between 9 and 20 solar masses. Now again, 20 solar masses is probably about the limit for what we think that stars can form without forming through mergers. So almost all the massive stars that are out there are in this range. You're going to get a few stars even heavier than that, but basically this is sort of the upper limit for stars that form the same way that our sun does. Now, stars heavier than 9 masses will also fuse hydrogen on the main sequence, just like the low mass cousins. However, again, these stars have core temperatures that are far too high for degenerate matter to form. Basically, the core is so hot that the electrons never get close enough together to form the degenerate matter that we see in white dwarfs. Therefore, basically, we don't get those flashes that we saw in the other stars. For instance, helium flashes in medium mass stars would produce stars on the horizontal branch, or the red clump. Carbon flashes would produce the end of the star for those oxygen, neon, magnesium white dwarfs. Okay? But again, at masses above 9 solar masses, the cores never get cool enough for the degenerate matter to form. So instead of hydrogen, instead what happens is that hydrogen fusion at the center is followed almost instantly by helium fusion. And the star will just basically move off the main sequence. Now when this happens, the star will basically go from an O-class main sequence star and move to the right and move upward, basically into being a B-class star, but much larger and much brighter. Again, the energy output of these blue supergiants might not be all that much greater than the output of the O-class star, but the blue supergiant will appear to be much brighter due to a slightly lower temperature and due to the fact that it puts more of its energy out in the visible part of the spectrum. Eventually, as a core gets hotter and as the core gets denser, it generates so much energy that it pushes the outer layers of the star further and further away from the center. This causes the outer layers to not only expand, but also cool. Again, the energy output of the core has to continuously increase, basically to offset the increase in energy density. This core isn't just sitting there static. The core is getting heavier and denser and heavier. And again, as it does so, it's got to put out more energy to support itself. The outer layers, again, experience even more outward pressure. So essentially, the additional energy can cause the outer layers to expand hundreds of times greater than even the radius of the sun. There are instances where a large star can become a supergiant, go from blue supergiant to red supergiant back to blue supergiant and oscillate back and forth. But it really depends on what's happening inside the star. A good example to find some of these supergiants and stars that will eventually become supergiants is actually the Constellation Orion. Now, we talked about the Constellation Orion earlier because the Constellation Orion was one of the locations of the best known stellar nurseries in our galaxy, the Great Orion Nebula. Okay? The Great Orion Nebula actually exists far beyond some of the stars that we see in Orion, which are supergiants. So there's no association between what's happening in the Orion Nebula and these stars. It's just sort of a coincidence. Now, here are some of the supergiants in the constellation Orion. Betelgeuse, Rigel, Saiph, Alnitak, Alnilam. Now, Mintaka is actually a bright giant star which is on its way to becoming a supergiant. And Bellatrix is another example of a giant star that will eventually become a supergiant. So all the major stars of Orion's sword and Orion's shoulders and Orion's knees are actually either supergiants right now or on their way to becoming supergiants. In fact, if you watch some of these, you could actually say that many of these stars sort of represent a progression from being on the main sequence, becoming supergiants, expanding larger and larger, and making it all the way to the red end of the spectrum. Let's start with Betelgeuse. It's the second brightest star in the constellation Orion. This star is actually an M21A red supergiant star. Now, the Roman numeral 1 means that it's a supergiant. The letter A means that it's an extremely bright supergiant. Now, its surface temperature is about 3,500 degrees Kelvin, and Betelgeuse's surface is so large that it would expand beyond the orbit of Jupiter if we placed it in our own solar system. Again, this star started with a similar mass as all the other stars in Orion that we see, but its surface is greatly expanded and significantly cooled as it's done so. So it's basically giving off similar light levels to the other stars. It's just that its surface has to be much larger to have the same stellar output. Rigel in some ways is sort of like a younger version of Betelgeuse. It is a brighter star, probably a little more massive than Betelgeuse, but basically Betelgeuse was probably a blue supergiant like Rigel at one time. Now, this star is a B81A blue supergiant. So that makes it actually sort of cool in terms of a B star with a surface temperature of 11,000 degrees Kelvin. Now, although Rigel is only 70 times bigger than our Sun, it is much smaller than Betelgeuse. Its very high surface temperature makes it brighter than Betelgeuse. By the way, Rigel actually has two smaller stars, Rigel B and C, which orbit it. Another example of a supergiant is Antares. Antares, like Betelgeuse, is a red supergiant. It's an M21A red supergiant, and its surface temperature is 3,500 degrees Kelvin. Antares is the brightest star in the constellation Scorpius, and if Antares were placed in our solar system, just like Betelgeuse, it would go beyond the orbit of Jupiter. It would engulf all the planets, including Jupiter, and leave only Saturn, Uranus, and Neptune. An example of a white supergiant, not quite as bright as Betelgeuse and Rigel, is Polaris. Now, Polaris is most famous for being a moderately bright star, almost exactly at the location of the North Celestial Pole. With Polaris, it is definitely white, F-class star, F7, so it's sort of white, almost yellowish. Surface temperature is 7,000 degrees. And Polaris, like Rigel, is actually a multiple star system with two smaller companions, just like Rigel. So there you have a white supergiant. Deneb is an extremely bright star. It almost reaches the classification of hypergiant, which is the brightest of all supergiants. Deneb is the brightest constellation in the star Cygnus, the Swan. It's one of the most luminous stars known, has an absolute magnitude of negative 8.73. The star is an A21A-0, and usually -0 indicates that, again, it's a hypergiant. Very hot surface temperature, 8,400 degrees Kelvin, and Deneb, if placed in our solar system, would extend beyond the orbit of Earth, but it puts out even more energy than Rigel or Betelgeuse. Now, after the star leaves the main sequence, remember, it starts out by fusing hydrogen. After it's created enough helium in the core, then the helium core kicks in. That fuses helium into carbon and oxygen. After the carbon core gets large enough, that begins to fuse carbon into even heavier elements, oxygen, neon, and magnesium. So after the carbon shell reaches a sufficient temperature, okay, we're forming these heavier and heavier elements. Really, the core is beginning to look like layers of an onion. The star is 9 times the mass of our sun. The carbon burning will only last about 380 years. That's a small fraction of the star's total life. For stars that are 20 times the mass of our sun, the carbon phase only lasts for 150 years. This is interesting to look at because really, successively, you get less energy out of each reaction. Hydrogen lasts for 90% of the star's life. Helium fusion lasts for basically almost the rest of the 10%. And then after helium fusion, any heavier fusion is going to take place in a much shorter period of time. By the time it's fusing carbon, the star's life is pretty much over. Now, oxygen is fused after carbon. Very rapidly, the carbon is converted to neon, magnesium, and oxygen. Then once the temperature reaches 2 billion degrees Kelvin, neon and oxygen begin to fuse. Okay? From this reaction, we produce even more magnesium, other elements such as phosphorus and sulfur. And a new core begins to form where an even heavier element, silicon, settles at the center. Now, this type of fusion can only last for a few months. Okay? Silicon fusion produces the heaviest of elements, and by the time we reach silicon, the star is pretty much on its way to die. The star, as it fuses silicon, is basically producing iron in the core, and iron is an element that will not release any energy if it's fused. So for silicon to fuse, the temperature actually has to reach about 3 billion degrees. Here's our problem. The star has been able to get away with fusing heavier and heavier elements for all of its life. When it ran out of hydrogen in the center, it started to fuse helium. When it ran out of helium, it began to fuse carbon. When it ran out of carbon in the center, oxygen took over. Now silicon has taken over, but you notice each of these bar graphs represents the amount of energy that we get. Okay? If you're getting less and less energy out of each reaction, that means that you run out of the fuel much faster. Again, hydrogen gives you the most amount of energy. Okay? Therefore, the star can spend most of its life fusing that. But as we go to progressively heavier elements and you get less energy out of them, that means that you're only going to be able to go on for a limited amount of time before you have to go to the next element. The problem is the final element in the series actually takes energy away. So if it began to fuse iron at the very end, it would actually cool the core and the core would collapse. So the last day in the life of the star, the last point before the star destroys itself, basically it's going to, on the outside, just look like a normal supergiant star. It might be a blue supergiant, it might be a red supergiant, it might be a hypergiant. it will be some type of, very large, very luminous star, probably star that's not all that stable. But what we can't see at the center is the star has basically built up a time bomb, and this thing is ready to go off at any moment. The iron core is in the last moment of the star's life, being heated by all the outer layers. But if that iron core gets heavy enough, the pressure on the nuclei, on the iron nuclei, is going to cause them to fuse. And again, when that happens, the iron core is just going to collapse out from under it, everything. Now again, this core is extremely dense, it's extremely hot. It's also under a tremendous amount of compressional force. Okay? Really, besides heat, the only thing that's going to support the iron core is the degeneracy pressure of the electrons. Okay? When we exceed the pressure that the electrons can support, the electrons are going to end up going into the nuclei and fusing with the protons. Essentially, the iron is going to fuse together, and the whole center of the star collapses underneath the overlying layers. Now, here's what happens. Think about all the iron nuclei. The nucleus has protons and neutrons. The protons in the nuclei are going to be shoved together with the electrons. When this happens, we produce two new types of particles. Now, there are already neutrons that are in the core. Okay? But a new type of particle, which is usually a byproduct of fusion, is going to be created at a very high rate. These are called neutrinos. Basically, the iron core falls out from underneath the star. Sort of like if you're sitting in a chair and somebody pulls it out from under you. This core is going to collapse. It's probably, at the time that it forms, many times bigger than the Earth. As it collapses, probably almost as large as the Sun, in fact. As it collapses, it's going to shrink to about the size of Manhattan. Okay? And as it comes falling inward, it's going to actually rebound and then bounce back. Basically, as it's collapsing, electrons and protons are merging, producing a huge generation of neutrinos. At the same time, a pressure wave is created as the core rebounds and bounces back. Now, what about these outerlying layers? There's nothing supporting them anymore. Remember, our iron core in the star used to be, I'm trying to draw this, I'm not doing a very good job, right about here. But now again, it's like sitting in a stool and somebody pulls it out from underneath you. There's nothing there, so all the outer layers begin to fall outward. So, at the same time, all the overlying layers are falling inward. This big wave of neutrinos is pushing its way outward, and the infalling and the outgoing matter is going to collide, producing a huge shock wave. Now, along the shock wave, there's a giant leap in both temperature and pressure. And wherever the shock wave goes, it's going to create a huge wave of fusion. It's going to basically make itself more and more intense as it propagates outward. Now, at the center of all this is a ball of neutrons, what we call a neutron star. All those iron atoms, once again, have fused together to produce this huge ball of neutrons. They basically have the density of a nucleus, but again, they're about the size of Manhattan, about 3 miles across. This core that's left over is called a neutron star, even though it's not a true star. It's so dense that really only the degeneracy pressure of not electrons, but neutrons supports it against the intense pull of gravity. These things are so bizarre that a teaspoon of matter from a neutron star basically has the same mass as a mountain. Neutron stars, again, are less than about the size of Manhattan or New York City. They're very bizarre structures. Again, they're not really stars. Their insides are basically collections of primarily neutrons and other heavy nuclei, and even the outside has a crust of perhaps elements that wouldn't naturally exist in nature. Now, basically, as a core collapsed, a neutron star formed at the center. But in the process, the outgoing shock wave is heating up all the lighter elements, fusing them into heavier elements, and is heading from the inside of the star to the outside. Basically, the shock wave makes it to the surface, blows the outer layers of the star left away, and leaves the neutron star behind. Essentially, what's happened here is that the star is turned into a huge nuclear bomb. The way that a hydrogen bomb works is it uses a nuclear reaction, usually a fission bomb, to superheat and compress some type of fusion fuel, like deuterium and tritium. If it gets it to a high enough temperature and high enough pressure, the lighter elements fuse into heavier elements. The outgoing shock wave from the collapse of the core has pretty much done the same thing. It's compressed all the matter in front of it, heated that matter, and created an even larger shock wave. So now we have this bomb, more massive than our own sun, basically blowing up and dumping a tremendous amount of matter into space. It's what we call a Type 2 supernova. Okay? It's called a Type 2 supernova as opposed to a Type 1 because it has strong hydrogen lines because the outer atmosphere is basically being blown into space, and that atmosphere is really made mostly out of hydrogen. Now, light from a supernova is initially created as the surface of the photosphere is heated to 500,000 degrees Kelvin. Now, later on, isotopes formed in this nuclear reaction are decaying and giving off energy, adding to the light of the star. One element or one isotope that's created in very high amounts is something called nickel-56. This is unstable, and it quickly decays into cobalt-56, which is also unstable. As it decays, it gives off a positron and a neutrino, and the positron will collide with other electrons, producing more energy. Now, when we look at the light of a Type 2 supernova, we see that, again, initially, the light is from the surface becoming very hot. Eventually, we see that the nickel-56 decays with time. That nickel-56 then decays into cobalt-56, which then decays itself, and that causes the light curve to continue to decrease with time. There are two basic types of Type 2 supernovas that we oftentimes see. One, which has a light curve, which is shown in green here, and the other one that has this little step here. And basically, that's due to an envelope of gas around the star. Remember, these stars had very high stellar winds, finally becoming transparent to the decaying light behind it. Now, one recent supernova that we've been able to observe is SN 1987A. As its name implies, the supernova took place in 1987. It was at first a blue supergiant. It did not occur in our galaxy. It actually occurred in a neighboring galaxy by the name of the Large Magellanic Cloud. The supernova was so bright, and even though it was in another galaxy, it was easily observed by the naked eye. Now, this is what the light curve looks like. The initial spike in intensity, again, was due to the surface of the star becoming very hot, basically the recombination of ionized hydrogen, and then the decay of nickel-56. Nickel-56, again, was the result of the huge thermonuclear reaction that took place, generating the energy for the supernova explosion. Eventually, that decayed into cobalt-56, and that was responsible for much of the light that you see down here. Here's an actual picture of the supernova, and what you can see here is rings of material which were given off long before the supernova actually exploded. I didn't do a good job drawing that. You got one ring up here, you got another ring right here. Okay? The ring that's of interest, however, is this shock wave. Again, didn't do a good job with that, which is propagating outward. That's the actual explosion. We can see at the very center of it the gas that still surrounds the dead neutron star where the star blew up. Now, once again, the life of a star, up to about 20 solar masses, from about 9 to 20 solar masses, is basically pretty straightforward. It fuses lighter elements into heavier elements, keeps going up the periodic table until it reaches iron. Once it reaches iron in the core collapses. It leaves behind a neutron star. Stars heavier than this, however, may experience a different type of evolution. Stars between 20 and 40 solar masses don't end their lives as red or blue supergiants like we saw in the previous case. Instead, what happens is their cores become so hot that thermal pressure is so great, even before the star ends its life, it rips off the outer layers of the star, and the outer layers are blown into space. These strange stars have no hydrogen in them. They're actually stars that are completely made out of helium and heavier elements. And after ripping out the outer layers, these stars can actually be even hotter than O-class stars. They're called Wolf-Rayet stars. Again, basically, what we've seen here is the inner layers of the star are now exposed. The outer layers have been blown out into space. So we have a core surrounded by the middle layers. And again, these stars were first discovered to be unusual because they had very strong helium emission lines. Again, the stars range in temperature from anywhere from 25,000 degrees Kelvin up to about 50,000 degrees Kelvin. Here's an example of one of these stars. WR, standing for Wolf-Rayet, named after the founders of the star, 124. And you can see here that this star is surrounded by a nebula. This is the gas that actually was blown into space. This is actually an infrared image of the star. And you can see the very large amount of material which has been ejected by the star. Now, stars of this mass, from about 20 to 25 times the mass of the Sun, if it does have time to reach the red supergiant phase before the outer layers of hydrogen are blown away, it may go through a supergiant phase. But usually if it reaches the Wolf-Rayet phase, it'll just and its life soon after blowing out the outer layers. Again, the core of the star will proceed fusing heavier and heavier elements. And again, when the star's iron core gets large enough, the core collapses, producing a huge thermonuclear explosion. Now, the problem here is there's no hydrogen left in the atmosphere. It's already become this wolf-rayet star. So what's left over is this shock wave blasting through the helium. And this produces a very different spectra than what we see with the type 2 supernovas. We call these type 1b supernova for type 1, meaning that there's no hydrogen lines present. Now, this type of supernova is thought to be a type 1b supernova, where the remnant could be a neutron star. However, some say that such a supernova could also leave behind a black hole. Now, stars between 25 solar masses and 120 solar masses leave behind the most extreme of all objects. The evolution of these stars is really so fast that they reach this wolf-rayet phase almost immediately after reaching the main sequence. Now, unlike stars that start with less than 25 solar masses, these can be so unstable that in their cores that they never really have a constant output, or will go through phases where they're producing huge bursts of energy. Now, like other massive stars, they will proceed to produce progressively heavier elements. The heaviest elements will fuse at the center, while the lighter elements will fuse in the surrounding layers. But unlike stars that start with less than 25 solar masses, the core is so massive that even the neutron degeneracy pressure is not going to support against the pressure of gravity. This is what we call collapsars. The dead iron star, the dead iron core, is so massive that it collapses into a singularity, an object that has infinite density, or commonly we call this a black hole. This type of star basically destroys itself where the core becomes a black hole, and the infalling layers of material are initially sucked inward and then blasted out. The black hole was once the nuclear core of the star. It actually supported the overlying weight of the star. Now it's essentially consuming the star as the star destroys itself. Basically, the iron core, or what was the iron core, is now the black hole, it begins to suck in all the matter that's around it nearly at the speed of light. However, the outer layers of the star are so far removed from the center that the outside of the star may initially appear to be completely normal for a few moments after this has taken place. Again, as the matter falls inward, the rotational inertia of the black hole causes it to spin faster and faster. And the black hole accretes matter and basically converts a lot of the infalling matter, so matter falls inward, into pure energy, and generates two high-energy jets in the direction of the poles of the star. These jets begin to blast their way to the surface, and as they make it through the star, they generate something called a gamma ray burst. These high-energy beams blasting their way through the star come in contact with other matter that the star has previously given off. This generates a very large shock wave, which in turn generates an intense beam of gamma rays. Eventually, the star destroys itself as the shock wave makes its way through the rest of the star, producing a very intense supernova we call a hypernova, which also has intense beams of energy coming out through the polar regions, which we call a gamma ray burst. So basically, with massive stars, there are two basic ends that these stars can meet. The most common end, for the lightest, is the generation of a neutron star as the star explodes, producing a supernova. For the lower mass stars, they still have their layers of hydrogen. They'll produce a type 2 supernova. And these are the most common types of supernova for the massive stars. If it's even more massive, it would have given off of its layers of hydrogen. In this case, it would be a type 1 supernova. For the most extreme cases, instead of getting a normal supernova, we can get an explosion that's hundreds of times even larger, what we call a hypernova. When these hypernovae are generated, what is left behind is probably the most bizarre object of all in our universe, and that is a black hole. Let's go over some exotic phases that some of these stars go through. Stars with masses greater than 85 solar masses will actually enter a phase before their end, known as a luminous blue variable. These are some of the brightest stars in the universe, and Eta Carinae is a very good example of a luminous blue variable, which is thought to be 120 times more massive than the Sun. We think that Eta Carinae actually puts out 5,000 times more energy than our own Sun, and it's actually experienced many smaller eruptions. It's thought that the star is unstable and will eventually destroy itself as a hypernova explosion, a very intense supernova explosion. So Eta Carinae is a luminous blue variable. Again, some of the brightest and most massive stars known. Another interesting phase is what's called a hypergiant phase. Luminous blue variables are some of the brightest stars, but the hypergiants are actually some of the largest stars. For instance, Rho Cassiopeia is a very rare yellow hypergiant. You can easily see it with the naked eye in the constellation Cassiopeia. It's thought to be about 500,000 times more luminous than the Sun, and its mass is probably about 40 times more greater than our own Sun. Probably was a luminous blue variable before it became this, and will continue to expand and cool. VY Canis Majoris is another example of a hypergiant, except for this is a red hypergiant. We can see VY Canis Majoris and Mu Cephei compared to normal, if you can call them normal, red supergiants, Betelgeuse and Antares. And again, Mu Cephei in the constellation Cephus has a radius of 1,420 times greater than our own Sun. Just as sort of a side note, stars that are even more massive than Eta Carinae are no longer thought to form, but can actually meet an end before they even are able to generate enough iron in their core to create a core collapse. between 120 times the mass of the Sun and 220 times the mass of the Sun, 260 times the mass of the Sun. These stars will actually self-destruct through a process called Pear Production. Before the core can fuse its heaviest elements, the temperature gets so hot that gamma rays are created. And the gamma rays actually create matter and antimatter. Now, usually, what will happen is a nuclear reaction is going to generate heat, and the heat's going to support the star. However, with these pair production instability stars, instead of generating the needed heat, they generate matter. And without any support, the core actually collapses, and this causes the outer layers to also implode. Unfortunately, the star basically blows itself out of existence. And although it creates a tremendous amount of heavy elements, there's no remnant left behind. We think that a supernova, SN 2006 GY, which happened in a very, very distant galaxy, and therefore it happened a long time ago, is an excellent candidate for this type of supernova. Now, pair instability supernovas are thought to look like typical type 2 supernovas, but this one was 100 times brighter, indicating that it wasn't being created by the same mechanism. Additionally, the light curve was very, very different too. Theoretically, any stars greater than 260 times the mass of the Sun would be very difficult to create in today's universe. Might have been much more common about 10 to 12 billion years ago. But these types of stars would basically destroy themselves, not through pair production, but through a process called photodissociation. Basically, the interiors of the stars would be so hot that not only would they produce matter and antimatter, the gamma rays would tear apart the nuclei of the stars. It would basically shut down nuclear fusion. The core would implode, probably leaving behind a black hole. So once again, the end of these stars can be very, very complicated. There are a number of different complex processes that they can follow. So let me summarize the basic ideas here. The heaviest stars are able to fuse some of the heaviest elements. It can fuse elements all the way up to the element iron. Okay? All of these stars end their lives through some type of catastrophic event. Okay? Usually a supernova. The heavier the star, the more dramatic its end might be. So the heavy stars, again, they go on the main sequence, typically just like our low mass and medium mass stars. Instead of becoming giant stars like the medium mass stars, they become supergiants. And instead of ending their lives as planetary nebula, leaving behind a white dwarf, they blow themselves up, leaving behind a neutron star, a black hole, or in some rare cases, they completely blow themselves up, leaving nothing behind.